My name is Amit Chauhan. I work for a company called DB, and have been working here about 3 years or so. And what we do is we build the distributed SQL database. And before coming to Yugabyte, I have done a lot of software development with apps like scaling petabytes of data at companies like Verizon, Charles Schwab, Shutterfly. So in nutshell, this is my experience. Personally, I live in Bay Area. I have been a long-term resident here, around 17 or 18 years or so. So today's talk track is how to weather the cloud systems with multi-region, multi-AZ airflow workflows. So let's get started on that. And so I have a packed agenda. Today we are going to discuss airflow as a distributed system. Then we are going to talk about the central role of a database, like the metadatabase, which Airflow choices it comes with. We'll discuss high availability, resilience, and horizontal scalability from Airflow perspective. And then I'm going to talk about why we should consider using distributed database instead of default choices, which comes built in with Airflow. And then I'm going to introduce you with Yugabyte DB, which is the place I work for. It's a distributed database and how it can help achieve or fill in some of the gaps I see with the current architecture. Then after that, we are going to do a little demo where I'm going to showcase integrating Airflow with Yugabyte DB, how easy to do that setup and how you can span your cluster across multi data centers or multi-regions even. And then time permitting, I'm going to talk about the internals of how the distributed database works, and resiliency and horizontal scalability, which will be part of the demo and the talk track. So to explain that, what is going under the hood, I'm going to talk about that as well. So now coming to existing components of Airflow. So the way I see it, there are 6 main things: scheduler, executor, workers, the queue, web server, and then of course the metadata database. As just as a refresher, scheduler is responsible for scheduling your tasks. Executor manages the task execution. Workers, they will execute your task in parallel. And then when you are using Celery executor, which will be the most of the times, which will be the case in the production environment. So using a queue like Redis or RabbitQ, and for managing the queues for these workers. So finally, web servers providing the interface for monitoring and managing DAGs. And lastly, a metadatabase. So storing your metadata about what DAG is running, task instances, logs, etc. Typically the solution here is Postgres or MySQL or SQLite. Let's talk about it. So very high level. This is the diagram I took from one of the wiki pages or of Airflow. If you have to deploy Airflow in a multi-DC type environment, so this is something it will look like. You will have different virtual machine or node instances where you will be running multiple Airflow schedulers. You will have one or more web servers, then multiple workers, and then on the right side you see some SQL database. So this slide I really want to highlight some key points here. And it's Airflow by default, it's architected to build to support distributed execution. So you can scale horizontally. There's no limitation from a scaling perspective. What does that mean? If you look at components one by one, schedulers, so multiple schedulers can be configured in a high availability setup. You can have, in previous diagram I was showing, you can have multiple schedulers running in 2 different availability zones, for example. Same goes for workers, executors, web servers. So all these components you can scale horizontally very easily. Just add new instances with your config, and they will be part of that distributed cluster. This last point, database, this is the question mark. With Postgres, as you know, we are going to discuss more on that, and most of the talk track will focus on this particular topic. So what are the default choices you get with Airflow? So you have PostgreSQL, MySQL, SQLite, all three awesome databases, and good choices. But so as you can see, if you look at the diagram on the right side, your database is the central and single source of truth here. So all your components, which we earlier highlighted, right, like a scheduler, executor, workers, web servers, and all, database is going to act as a single source of truth. So the metadata database, it will store all the critical information you have, like tag execution status, task dependencies, task log, etc. And it's a communication hub. Like every time, whatever activity is going on, all that information is going in that database, and that's how you're kind of distributing these different components. So, but now what happens if the DB goes down? Since it's a single source of truth, it will kind of occur in your scheduler failing, your workers will fail, and web server, of course, since all of the components are kind of dependent on that particular piece. So all the failure will occur from that perspective. Second thing which I want to highlight is with the default choices, you don't get a horizontal scalability. So you can, if you have a Postgres instance, you can scale it vertically, you can add more storage, more compute, but then there is a limit you are going to hit at some point, and you will need to do the manual sharding, create a new instance, and then manually move the data around. The second problem which comes is the replication. So replication, if you have a multi-DB setup, the replication becomes another challenging problem, especially if you have a setup across multi-regions or multi-AZs type environment. So double-clicking on this high availability part, achieving high availability, especially across multi-region layout, it's operationally challenging. And often, it can result in downtime of few to several minutes, even during planned maintenance. And so you can achieve it slightly with something like Patroni on Postgres. You can achieve the high availability, but it comes with the downtime cost. And if you are undergoing any maintenance work on your OS maintenance or database upgrade, your Airflow application will need to take that downtime. And really talking about replicating a traditional RDBMS across regions or zones is operationally it's not that easy. So what can we do about this? Since Airflow's reliance on a centralized metadata database introduces limitation in scalability, resilience, and performance, so as your workloads are growing, the database can become a bottleneck. And of course, as we saw, it can be a single point of failure. And so what we can do is we can transition to a distributed database solution, which can mitigate these challenges which we talked. And you can ensure the high availability, horizontal scalability. If you are able to plug in Airflow and replace the likes of Postgres or MySQL with some distributed DBs. So what are your choices? So when I talk about distributed SQL databases, especially, you have many solutions out there, Yugabyte DB is one, then you have TiDB, Google Spanner, from which most of these distributed SQL were basically born. And if you're using OSS Airflow and want something which is cloud agnostic, and 100% open source, Yugabyte DB can be a great choice. So it will work. It can be like a plug and play type thing. So it comes with Postgres driver. You will be able to reuse your existing Postgres driver. So this is the thing which I propose here, a new architecture. When you lay out your Airflow in your environment, so you have these different processes, multiple processes running across different nodes or different zones or different regions, and then replace the database. So which can provide you resilience, not just at the node level, but even at a zone level or a region level. Depends the way you lay it out. Additionally, like it comes with automatic failure, scalability, geographic redundancy. And I'm going to showcase like how easy it is to and what goes on internally to achieve these things. So at this point, like I just want to mention a few key things on Yugabyte DB. So if you look at the top right side, Postgres SQL compatibility, resilience, and high availability and horizontal scalability, these are kind of built in this database. And all that other good stuff like ACID transactions and security, geographic distributions. So and when I talk about the architecture of the database, I'm going to talk about how it is, what we did to make it Postgres SQL compatible. Again, to reiterate on the same thing, 100% open source, plug and play replacement for Postgres, no single point of failure for your metadata database. You can horizontally scale, you just add new nodes. It will do the automatic sharding, automatic rebalancing, so no need to do anything manually in here. It will be all done behind the scenes. And you can achieve like fault tolerance across regions, AZs. And the good thing is with distributed database, like you can get performance improvements. So if I have a 9-node database cluster, all the 9 nodes will be working equally hard. Unlike our traditional setup, RDBMS setup, where you have a master and a slave, like where master does all the writes and does a bunch of work in there. So like Airflow, depending on your need, like if you want to have a single region multi-zone, so you can lay out your database, this distributed database accordingly. Like you can have multi-AZ type setup, you can have a single cloud multi-region type setup, or you can even have like a multi-cloud multi-region. Like some companies which don't want to tie up their fortunes to one cloud, they are spreading out their environments across like a multi-cloud type environment. So meaning, and this cloud can be like your on-premises environment also. So you can have the cluster stretched across multiple different cloud providers or even your data centers. It does one thing, and this is very critical, that you cannot beat the laws of physics, right? Like, so network latency does come into play here. Meaning, what does that mean? So if it is like your cluster is in the same fault zone, like a node or a rack, latency is pretty low, like 1 millisecond, 2 milliseconds. But like if you are spreading it across single region multi-zone, then you might have to bear with little higher latency to like 3-4 milliseconds. And if you're going across the regions, like it can vary about like 30-40 milliseconds, like a East Coast, West Coast type thing. And of course, like with a global region, if you want to stretch your cluster where you have a part of the node sitting in United States and part in Europe and part in Australia, you are looking at like 200, 300 millisecond type latency. So that is one consideration to keep in back of your mind. Now, I want to talk a little bit about like setting up your Airflow with Yugabyte DB. So what does that entail? Like how difficult it is? All you need to do is change these 2 parameters to point it to your database. So in this example, which I'm showing, like I'm using the same driver like Postgres driver, and then I'm just plugging in that one of the host of Yugabyte cluster. So you don't need to give the details of all the cluster components. You give either the load balancer one or one of the host, and it will figure out the rest of the cluster automatically when it does the connection. So these 2 parameters, that's all you need to change. And one caveat which I wanted to mention here is that when you try it out, maybe today evening or later in your own environment, one thing which we need to do here is like there is a flag which you need to set in Yugabyte, like silence advisory logs not supported error log. So that is one caveat I wanted to mention here. But very soon we are working towards the PG parity, like we are, I think 97%, 98% compatible. But with the new releases, upcoming releases, we are going to fix this GitHub issue, and you won't be needing it in future. Just wanted to lay it out like for fun's sake. Like when you look at these different objects in which airflow creates. This one diagram here. So now we'll jump on to demo. And what we are going to do in the demo is we'll set up a Yugabyte DB cluster, multi-node, multi-AZ, and then we'll have two parts to the demo. Like first, I will showcase in the multi-AZ type scenario, and then I'm going to showcase in multi-region scenario. Show you like how easy it is to set up this airflow. And for resiliency testing, like what we'll do is I have these 3-node cluster. I'm going to bring down the entire availability zone. So meaning one node in one of the zones, and showcase like how this your airflow will still remain resilient. Like there will be zero impact to your airflow infrastructure. And then I will also discuss the high availability during planned and unplanned outages. So I created some of these examples, some of these scripts to create the cluster like in your own environment. I will share when I finish my presentation. I'm going to share that information with you as well. So you can easily go in and clone that and run those examples yourself. So what I'm doing is like I'm doing it in AWS. I have already created these 3 different nodes, Yugabyte 1, 2, 3, and you can see that they are spread across 3 availability zones, 1A, 1B, 1C, which is Virginia. And now I'm going to log into one of the servers, and just want to show you briefly this script. It will be in my GitHub. You will be able to check it out from there. And made it simple, like plug in your IPs, plug in your cloud information, and then once you run it, as long as the location of this script has a connectivity to those nodes, it's going to go download the software on each of the nodes. It is going to set up the cluster. So let's run this script and see what it does. So what I did is like I had already downloaded before recording this demo. So I am going to skip the setup in here. It is going to SSH into each of these nodes, and it's going to start the Yugabyte D process. And by the way, Yugabyte D is like I refer Yugabyte DB as Yugabyte D here because that's like our OSS offering which we have. We don't hide any capabilities, so you're free to download it and use it even in your production environments. So now I have restarted these 3 processes, and if I go to my UI, so you will see that there is a 3-node cluster spread across these 3 different zones. And if you click on the right side, like number of tablets, and which I'm going to talk about in more detail later, there is nothing out there. Like there is no operations happening currently. So now what we'll do is we'll log in to a place where I have this Airflow Docker Compose set up, and we are going to use one of these IPs so I can plug it in that configuration. But before that, I want to showcase like there is nothing in the database right now. When I went to Yugabyte DB, it looks very similar to Postgres. And I fire this function called select star from YB servers. It will show me the exact information what I showed you from the UI. It's a 3-node cluster. It's spread across single region, three zones. And this advisory lock message YB silence, I'm going to alter that role. And now I'm going to switch over to my machine where I have this Docker Compose process written. And this is the file which I use. I'm using the multi-AZ setup from the database side, but all these processes, these are going to run on the single node. So I'm not really like spreading out the Airflow processes currently for this demo. So all you need to do is to change the other things like services. I have kind of got rid of Postgres, and so that since that is not needed. So we are going to go now start this particular process. So let's do a Docker Compose and provide the file name and do a up. So now I'm going to it is going to start these different things. Like for queue purposes, it's doing Redis. Then it is going to initialize the database. Since you saw like that earlier, that database I didn't had anything, but now you can see that it has started creating these different tables in my database. So as I refresh, I see more and more. It should come around 70 something. Right now it's 46. So we'll wait for it now. the database migration is done, and it's going to go and do the start the other scheduler and web servers and other processes. So I'm going to quickly, I've recorded the demo and I'm fast forwarding it, kind of fast forward the boring stuff, right? Like it's a wait thing. So once this comes along, like we are going to go and open the Airflow multi-AZ URL, like where this thing is. Let's log in to this particular Airflow instance. And yeah, you will see your typical, I'm loading these examples once. I haven't written a separate DAG for this demo purpose. We are going to activate a couple of them so we can start seeing the traffic. So it is already doing some activity. If I refresh this screen, you will start seeing that read and writes are happening on each of the nodes. There are some number of tablets and leaders and followers, which shows on the right side. One critical thing is like you will see that all these three nodes are working together. It's like it is not a single node type thing. So it is all these nodes are participating during this workflow. So let's switch on some of the activate couple of DAGs in here to generate more activities, and we'll refresh more. Like so you see like now once I do that, like your read and will increase, and if I refresh again, like I might see some more writes also happening. So it's a small workload. These with the two of the stuff. So you will see that usage wise and other things, like it's not doing much, but it's more for example purpose, right? Like what's the CPU usage, and if you look at the live queries, there are some live queries which are happening through Airflow. You will see that information in here. And again, like this is so what now we want to do here is we want to go and fail over one of the nodes. So far so good, like everything is looking good from Airflow perspective, and we are going to go to the AWS, and we are going to bring down one of the nodes. We'll shut it down completely. So we'll pick, for example, one of node 3. So Yugabyte 3. I'm going to go and just cold shut it down from here. So and then I will showcase like what happens. Like even your node went down, there is no impact. And we are going to deep dive into looking like what really happens behind the scenes when you do that. So I'm going to keep refreshing and see like once that server is out of commission. So let's refresh. So it's still not out. Like I'm going to do it a couple more times and quickly, and then we'll see that node when it is taken out. So it is still stopping. It's for some reason like it is taking a little more time to stop. Now I see it's gone, like because I have the instance running, right? So I will remove that and show that it's gone. And I'm going to refresh it. Now you see that third node is gone, and if I refresh my Yugabyte cluster UI, that whole zone is gone. So all the leaders will shift to the other two nodes from that particular guy. But if you look at your Airflow, I took out the entire zone. So this is the powerful idea here. So same concept will apply for the regions, like multi-region setup also. But I took out the whole AZ. There was a problem, whole AZ went down. The Yugabyte behind the scene kind of did the rebalancing or switched over the leaders within 3 seconds. We have a RTO of 3 seconds in which we'll shift the traffic to the other nodes. So now as a little 1 more minute demo, what I want to do is like I want to showcase like Airflow setup with 3 node multi-region Yugabyte DB. So this will be more of like a fast forward type thing, because I don't want to bore you with the same details. But for this, like I didn't want to set up the VPC pairing in across multi-region. So I went to our cloud offering and I created this Airflow multi-region. So if you look at in here, that it can tolerate the whole region failure. So I have it North Virginia, Ohio, and Oregon. The cluster is spread across 3 different regions in here. And right now it's just sitting empty. There is no read or writes happening. One difference here is since my application is in Virginia. So in Yugabyte gives you this option that you can have your preferred leaders sit in particular node, particular region or AZ. So I have set it up as the Virginia in this case. So I'm going to go quickly start this Docker compose process, and all this will be fast forwarded. So it will go rather quickly in here. But the same concept will sort of apply here. Critical thing is, like, I was talking to somebody, and they have a large, very huge infrastructure, like 10,000s of server instances, and at every given time there is maintenance, like OS patching or something going on in each of these nodes. So it is kind of critical, like not just about in failure type scenarios, but even during other planned outages also, to make your airflow sort of like very resilient. So same example, switching over some of these things, and this one I won't go and scale the cluster, but if you had to scale the cluster, it's pretty straightforward to do it. Like you if you're in the cloud, like you just have a couple of buttons to click, but on your OSs you just add new nodes to it and make it join the existing nodes, and it's going to do the rebalancing and all that good stuff for you automatically. So now we wanted to give you some idea, like when I was doing all this activity, which you saw, like what happens behind the scenes here. So looking at the high level architecture, like the very first thing which you might have noticed, that how I was able to use that Postgres driver. I didn't have to switch to another driver. So the reason for that is, like when we built our Yugabyte DB database, for the top layer, we forked the Postgres query layer. So any client or any driver which works with Postgres, it's a plug and play for Yugabyte DB. But under the hood, like if you look at the storage layer, this is our kind of like our bread and butter. So this is the part which is built, what we call DocDB, and it's responsible for automatic sharding, load balancing, distributed transactions, and we use Raft consensus for achieving that. And the other thing is, you're not restricted by, it's cloud agnostic. You can run it on any cloud, you can run it on Kubernetes, you can run it on-premises data centers. Very high level, when you install this software, so you will notice that on each node, like there are two processes running. Actually, this master will run based on the number of replication factor you have. So in this case, I have a replication factor of 3, so it will run 3 processes across these multi nodes, which can be, each node can sit in different region or AZ. Then you have this critical piece, YBT server, what I call, like which is responsible for all the transaction storage, sharding, and all that good stuff. Just to build on basics, like if you want to distribute the data, how do you do that? Let's say I have a table which I was showing you, like 70 different tables in there, right? So you take a table, you split into set of rows, and we call them tablets, you can call them shard, and then we go and put it on we split it, distribute it across the different nodes. And to showcase, like I'm showing it as only a couple of tablets. In production environment, it will be like much more. So you have these different tablets sitting in different regions. And I mentioned briefly about the Raft algorithm, right? So we heavily use it to do that application. So in the example which I was showing you, so I had these 3 nodes, right? And so for a given tablet, there will be a leader and the other guys will be a follower. And so each of the nodes will have some leaders, some followers. You will have 3 copies of the data, like if you are doing a RF of 3. And this leader election keeps changing also. So it is not that something, it's fixed. So in this example, like if I look in the middle, where what I call like a tablet leader, that yellow color tablet leader, you will see that each guy will have a follower in the other zones. And any read which happens, it happens from the leader. Any write which will happen will come to the leader, and it will do a Raft replication for writes and inserts and updates to the followers. Once it gets the majority confirmation, then only it will commit the data. So that's how we can achieve like a RPO of 0. So we are like 100% like a transactional database. So you might ask, like, what in the example you saw that like one of the node failed, right? So what happens is, like, as soon as that one node fails, so Raft algorithm, which I showed in previous slide, it is going to elect a new leader within 3 seconds. So this yellow guy had followers on the other dotted one. So there will be a re-election happen. Other guy will become leader. It will start taking the traffic. Rest of the nodes, since they are functional, so they will keep functioning as early previously. And this node which had some followers, like this purple guy, so it was not responsible anyway. So the purple one, the leader was on this node 3. So that guy was taking all that workload from here. And since you still have 2 copies, like a majority, so your system will keep working, is still working on that. So it comes like one other thing which is beautiful about the distributed database is what happens if this node, let's say it went down during the night time, right? So by default, and it's a configurable thing, that what it will do is that if there is a capacity in the other nodes in the zone, it's going to replicate the third copy of the data from the node which went down. And same concept kind of applies for the whole zone. Like you don't have to, like it's not just one node which went down, like your whole zone can go down and the leaders will shift to the rebalance to the other zones. Similarly, like if I have to scale the cluster, all you need to do is add new nodes. DBMS will take care of rebalancing, automatic splitting the tablets and spreading it across. So you don't have to do anything manually. If I have to say like architecture of Airflow, it allows you to, in this architecture which I was proposing, so you can easily consume distributed database. And with minimal, as you saw, like with minimal change, you can make your Airflow cluster truly resilient and horizontally scalable, even in multi-zone or multi-region setup. And this is something which we worked with different companies, and we have like 2 major providers who have these around hundreds of clusters, Airflow clusters running in their on-prem environment with this open source Yugabyte DB setup. So it's not just some theoretical thing, it's a proven thing. It's out there, out there in production. So, and if you have any follow-up questions, you can reach out to me on LinkedIn or via email. And this is the GitHub where I created these utilities. If you want to run this thing locally on your MacBook, like just clone that thing, and there are a couple of scripts which you can easily run. I have it documented how to do that. So it's within 15-20 minutes you can set up a Yugabyte DB cluster on your local machine and run these tests, like bringing down the nodes, scaling the cluster, and seeing it in actions.